Thanks for joining this video today, which is about dynamic security assessment. So the learning objectives for today are A, to explain the concept of security assessment, and B, to explain the basics of supervised classification for security assessment. So firstly, why do we need security assessment? The power system is ever expanding at this moment, as we integrate more renewable energy into the system. This renewable energy is weather dependent, resulting in more uncertainty of the power system. For instance, wind power is challenging to predict for the next few hours or the next few weeks. At the same time, we interconnect different countries and different regions, which increases the complexity of the power system. A critical challenge for system operators who are in charge of operating the power system is to know beforehand if a disturbance or an equipment failure will result in continuation and secure operation of the power system. The frequency has to be measured since deviations can result in a power system collapse. We call this a power system blackout or a partial blackout, which is the worst outcome for the power system and its operators. Dynamic security assessment, or short DSA, is the tool to investigate if such operating conditions and scenarios would result in insecure operations and possibly lead to blackouts. That is essentially what security assessment is about. So it's really about investigating whether individual equipment failures, such as generators or substations or transmission line, or if the interconnector fails, what the impact on the grid will be. Dynamic security assessment studies if those failures result in a secure or an insecure operation. There are two challenges with assessing the dynamic security for the future, where this assessment should be done in real time, both in the present and the future. The first challenge is that the future is highly uncertain, meaning that many possible trajectories and operating conditions of the individual power outputs are forecasted. For instance, the power of a wind park is highly uncertain. All these different operating conditions must be assessed. This means that the possible trajectories must be considered, all of them. All operating conditions should be evaluated and assessed. This has large computational costs as each condition requires a time domain simulation, which is computationally expensive. The second challenge is that this problem is high dimensional, meaning it is not only one variable that is uncertain, it needs to be forecasted, but it's thousands of variables. The power system, let's say a national system such as in the Netherlands, has several wind parks and thousands of photovoltaic modules. All of these have their own power output and require individual forecasts. They are all uncertain, and from a system perspective, this uncertainty becomes harder to manage. This forms a key challenge as uncertainty is difficult to estimate. So how can we manage to analyze such large amounts of data? Supervised classification represents a promising set of methods to avoid analyzing all of these operating conditions with real-time simulators. The idea is to train long before real-time operation and based on secure and insecure conditions, a classifier. So to train that classifier that can classify or separate security from insecurity. The features are the dimensions of the power system variables. The power of a generator could be one of the features. Think about a wind park that generates power. If the generator's power is very high, we may expect that the power system under a lot of stress. So the system or equipment failures are more likely to lead to power blackouts than when the power of the generator is low or it's lower. Therefore, we try to learn a decision boundary before real-time operation and then use this trained decision boundary to classify green from red, to separate secure from insecure operating conditions. That is, in essence, the goal. To derive such a classifier, the idea is to generate data beforehand of suitable operating conditions that are likely to occur in real-time operation, and then train the model based on this offline generated data. The model here represents the decision boundary. Then we perform selection and evaluation of the model. We always need to consider and modify the model if, for instance, the power system itself changes. But what are the features of a good model and how to train such a model? It is crucial to understand that system operators are human in charge of a large power system, and any tools to be used in the control room should be interpretable This means that an operator needs to understand how the tools function, to understand this model's input and output relationships and its features. At the same time, we would like to have a highly accurate model because it is a sensitive task to ensure the security of a power system. Accuracy becomes important when using machine learning models. These models are trained from data, meaning that if the real-time condition is very different to the training data, we can hardly guarantee the accuracy of the models. So it is vital to have accurate and interpretable models. An example of an interpretable model is a decision tree. There we have the decision tree structure, where the power system operating condition is going through the decision tree structure. The decision tree structure consists of split nodes that determine if the path is followed to the left or right, depending on a single threshold. Finally, the operating condition ends up in one of the leaf nodes, and a label for security or insecurity can be assigned. The ending leaf nodes are representing either secure or insecure operating conditions. Accuracy, specifically for DSA, is a significant subject. The accuracy is the correctly predicted operating conditions divided by the total number of conditions. However, sometimes it is worse to predict one class more inaccurate than the other. For instance, in DSA, to miss an alarm for insecurity is significantly worse than having a false alarm. For false alarms, we perform further analysis and place preventive control actions, but a missed alarm could lead to a total power blackout of the system. That is why we use the confusion matrix to distinguish these. There are two types of correct and two types of wrong predictions. We call these true positives and true negatives, and false positives and false negatives. So true positives and true negatives are good because we have made accurate predictions with the classifier. So it means that the actual class, let's say a secure operating condition, was predicted by the classifier as secure. This is what we call a true positive. A true negative would be if an insecure operating condition were predicted as insecure. But then there are two inaccurate classes, false positives and false negatives. One of them is worse than the other. A false positive means that an insecure operating condition was predicted as secure. This can be severe because if we are predicting a safety critical metric of a power system, we must not miss an alarm. If we miss the alarm, then a power blackout may occur. A false negative means there was a false alarm, which is not as catastrophic as a false positive. To summarize, this video discussed the importance of the security assessment and also showed how we train decision boundaries. We also covered the importance of training the models with different objectives, such as interpretability and accuracy. Finally, we introduced the accuracy and confusion matrix as metrics to evaluate classifiers. Thank you for joining today.